Welcome to this lesson on forces in two dimensions. We are getting towards the end of the forces and space scheme of work. This is lesson 18. And this is where we really are going beyond what's usually covered at Key Stage 3. But I think it's important because it's really going to set the stage for students to think really deeply about forces when they get to Key Stage 4 and Key Stage 5. And again, I don't think conceptually there's anything really in these next couple of lessons that goes beyond our core concepts. Pardon me, that is Newton's first and second law about how forces affect motion of objects. And yeah, there's just lots and lots of nice examples that again really get students thinking in terms of those concepts. So the first example that I would go through with students is the one about a rocket. So I'm going to draw my rocket here. We can draw a kind of cartoony type rocket, something like that. So there's my rocket going upwards, and the first thing we want to do is label the forces. Now yeah, I need to think carefully about how I colour code this, because what I'm going to do in a sec is transpose this into another diagram to show another way of thinking about resultant force. So what I'm going to do here is draw my point in the middle of my object, which is where the forces can be thought to act from. And I'm going to draw something up here. And what we're going to start doing today is thinking about this in terms of scale. So I might say, okay, I'm going to do a 2.5 centimetre line like this. And we're starting in one dimension actually here, you may notice, and then we're going to transition to 2 dimensions in a minute. So I'm going to draw a 2.5 centimetre line. You can change the length of that. That doesn't really matter too much. That's going to be the thrust provided by the rocket's engines. And then I'm going to draw the 2 forces that are acting downwards, the 2 main forces, and I'm going to make them both 1 centimetre long, just for simplicity. So one of those is going to be the weight, which I'll label as a W, and the other one is going to be drag forces. So air resistance and things like that. So I'll draw that, and that'll also be 1 centimetre. I'll label that with a D for, I'll just call that drag. Now, this is nothing new. I think students already drew this in maybe the unbalanced forces lesson. We've asked them to draw this already, so we're building on their prior knowledge. What we're going to introduce this time, though, is a new way of thinking about resultant force. And we can say, well, okay, let's say we've drawn this to scale, and this is 2,500 newtons. That was 2.5 centimetres. The weight is 1,000 newtons, and the drag is 1,000 newtons. Now, what we can do, instead of just doing the maths like we've done before, where we say, okay, let's take this direction as positive, and then kind of add them up with numbers and so on, is we can actually do a diagram. So what we can do is draw our upwards force like this. And then we can draw the other 2 forces with each, the start of the arrow for each force starting from the end of the previous arrow. So then I can come downwards here, and I had one force acting downwards like this. So this was the, maybe I should label these, this was the thrust here. This one here, let's call the weight. And then we had another 1,000 Newton, let's call it 1 centimetre force, which was the drag. Now, the point here is, when you draw these 3 forces, starting each force from the arrowhead of the previous one, you don't get back to where you started. And in that case, what that means is that this difference here, this is the resultant force. If, when you go through this exercise, your arrows don't get back to where they started, that means there's a resultant force acting. And I'm sure students will be able to spot, if you were to do the maths, the kind of equation method of this, adding and subtracting, you'd say, well, it's plus 2,500 minus 1,000 minus 1,000. So you've got a resultant force here of plus 500 newtons. So what that means is this rocket is going to accelerate upwards like this. Now, the next example was to say, okay, what I'm going to do next, or what the rocket does next, is switch on some boosters. So we're going to draw a very similar rocket like this. It's going a bit sideways, but never mind. I'm going to draw my centre of mass in the middle. Not necessarily going to call it centre of mass. Then I'm going to draw my 2,500 Newton thrust force. So I'm going to I'll put it as TH actually for thrust, so we don't confuse it with tension. It's going to be 2,500 newtons. I can draw my weight and my drag. I'll keep them the same for now. So they're both going to be 1,000 newtons. So that's W equals 1,000, and the drag equals 1,000 newtons. But this time we've set off some boosters. So maybe going in that direction, and that creates a force like this. So let's say that's another force of 1,000 newtons that goes like this. So it'd be worth questioning students in this case, what's going to happen next? In which direction is the rocket going to accelerate? And what you want them to recognize is that because you've got this extra one, we should end up with some sort of diagonal acceleration. And we can show that using the method that we looked at before. So if I start again, and let's do a 2.5 centimeter line for the thrust. That would be the thrust force. It's going to be easier rather than kind of going down and then across, I think, to go across and then down. So next I'm going to do, oh, sorry, I should have put, let's call that the booster force. I'll put booster, we can call it B in the next diagram. So that's the booster force. So next I'm going to draw this booster force, which is 1,000 newtons, and I should have labelled that on my diagram. It's B, which is 1,000 newtons. And then I've got my other two forces here, the weight and the drag, so I'm going to do here, and I'm going to label those the weight and the drag. And this means I've got a resultant force from the start of the first arrow that I drew to the end of the last arrow. I've now got a resultant force in a diagonal direction. So what that means is, instead of my acceleration, which perhaps I should have labelled on this one, in this one we've got an acceleration upwards, like this, because we've got a resultant force upwards, like this. Well, in this one, I've got a resultant force in that direction, and therefore I'm going to have, my rocket is going to accelerate parallel to that, so I'll draw it like this, in that direction. This is going to be my acceleration. And this kind of makes sense. If you have a force pushing you sideways, but you've also got forces pushing you up, well, you're going to end up in a diagonal direction. But what's really valuable here is that students are starting to think about this in a bit more of a rigorous, systematic way. Now, when they get to, when students get to GCSE and A level, they could calculate the size of this force. So I've done a very, very simple scale diagram here. So one way of doing this might be to say, well, okay, this is about 1.2 centimeters long. We said 1 centimeter was 1,000 newtons, so 1.2 centimeters is going to be about 1,200 newtons. They can also do it trigonometrically. We're not going to worry about the size of the force in this lesson. This is Key Stage 3. We want to keep the maths out of it wherever possible. We're really just getting them to think about what forces are acting and in what direction. And of course, what's the effect on motion, rather than putting numbers on it. That's the kind of thing that comes later. So I can just sketch one more example. That's to do with aeroplanes. So I'll try and do this quickly. So we can draw our aeroplane. And the first part of this task was to draw, this is my not very well drawn aeroplane. First part of the task was to draw the four forces acting when the aeroplane's travelling at constant speed. And I'm going to do these in pencil actually. So what we've got here is, I'm not going to do this to scale. In fact, I should do this to scale, then we can keep it accurate. So what we can do here is say, well, okay, let's imagine we've got 1,000 newtons down, 1,000 newtons up. And again, if students aren't that confident with the idea of scale, it doesn't really matter too much. The main thing is that they can see how we represent forces in more than one dimension. And let's imagine we've got, I don't know, 1500 newtons in either way, a 1.5 centimetre line. Now what you want them to notice here, in this first example, this is just moving at a constant speed. Well, therefore the forces must be balanced. And what you notice is, if we follow our method here, it's also worth labelling these forces, by the way. So that's going to be the thrust force, that's going to be the weight, that's going to be the drag. This is a force called lift. That may be new to them, and they're going to need that in the later examples. When we follow our method and we draw our forces, so we can do the 1000 newtons up, across, 1000 newtons down, drag, which is 1500 newtons, going back that way. What you see here is, if I label these L, thrust, weight, drag, well, the force arrows get back to where they started. That means there is no resultant force. And that's worth emphasizing, that if we make a closed loop with our force arrows, then there is no resultant force. And that's why the aeroplane travels at a constant speed. The final example is where the lift is reduced. So those little things in the aeroplane wings can move up and down to change the amount of lift. So let's draw another aeroplane. This time the lift is going to be a lot less. So apologies, it's quite a slow process doing this, but it's worth taking your time and modelling it properly with students so they see what's going on. So let's just do a very small lift here, like this now. And how many was that? That was 4 millimeters. And then we can do our 1.5 and 1.5. This. If we label those forces, so L, TH, W, and D, when we do this, we have a short lift. So let's start with the lift again. That goes like that. We've got the same thrust force, like that. Got the same weight, so that was 1 centimetre, 1000 newtons. That goes like that. And we've got the same thrust. So if this was to happen, what we would end up with is that there'd be a result force downwards, and therefore the object would start to move downwards. Now I've just drawn that and I realised that doesn't look mega realistic. I was expecting to have something like that, so I would need to think about that. Why it is that happens. But anyway, hopefully that's a nice way of illustrating the method that we're using here. And what you'll see is that there are lots and lots more examples getting students thinking about forces in these two dimensions. Pardon me. One last thing to say, at the end of this lesson, there is another section which is a bit harder. That's kind of doing the opposite process, which is turning diagonal forces, a bit like the one we had here, into horizontal and vertical components, what we call resolving forces. That is something that I think is to be reserved for classes who are super confident and are going to be able to deal with that, because it's quite a counterintuitive way of thinking. But there are some examples there that you can have a look through if you've got a class that's really, really keen to push themselves further. Okay, next lesson we'll look at projectiles.